Hi, and welcome to this Elos webinar. We are very happy that you would join us. My name is Casper. I'm the Dental Product Manager here at Elos, and I'm with Ralph, my good colleague.
Thank you, Casper, for the introduction. As Casper stated, my name is Ralph Erhard. I'm Master Dental Technician, and I'm working as a Senior Manager for Sales and Technical Support in Germany. And I'm happy to join the webinar today.
Great. You for sure bring a lot of experience, and we're going to need that today. Shortly about Elos. So Elos is a medical device manufacturer. We are serving not only dental, but also orthopedics and life science. We have 5 production facilities in 3 different continents. We have China, we have US, we have Sweden and Denmark. All the dental products are developed and manufactured in Denmark. So Ralph, what are we going to talk about today?
In the center of everything, it's the open workflow, what we are discussing today.
Yeah.
But more specific, we are discussing about the PMA today. So open workflow connecting with our PMA means to enable our customers to use our products in an open CAD/CAM environment, not just in a limited special constellation of hard and software environment. So I think that's the idea of open workflow. And as we stated, one part of this is the PMA as a product we use in this open workflow.
Perfect. Let's have a look at the agenda. So we have the Elos Accurate Analog for printed models. This is the agenda that we're going to talk about. So I think we have a really good topic here at hand. We're going to start a little about what is a PMA.
Yes, I think that's the basic point. What is a PMA? Yes, so the first point is to go into the actual use of this PMA, which is the printed model analog. So it's an analog, a physical part to transfer the implant position from the intraoral scan to a digital model, which you can print later.
Yeah. And then we have a little bit about the plaster model versus the printed model, because I guess you can't really compare these two. I think that's what we're going to cover here. Then we have a little bit about the history, because this is actually not the first analog or PMA that we had. We actually had a previous version as well. And we're just going to touch base a little bit about what actually happened. And that's a little bit to do with the technology.
Yeah.
And then some development on how we actually develop the actual physical product and the history behind that. And then the more technical part of it. How does it actually work?
Yes, sure. It's just about installing the PMA in the model, yes, to show if we need any auxiliary parts or tools for installing it, yes. And the last section is for sure, as the last webinar, the tips and tricks section, which means we want to show you how to create your own settings or to modify your settings right in the CAD software to enable you to print a very accurate model in your 3D printing process.
Perfect. I know you got a lot of interesting stuff for us.
Yeah, I hope so.
Yeah. And as Ralph mentioned, this is actually our second webinar. If you haven't seen the first one, this was on libraries. Make sure to look it up and have a look at it. We encourage you to do so. But let's get started.
Yeah. So I think, as you mentioned, we did a first webinar about the libraries, and this also starts a little bit with the library. Maybe you remember if you participate the last webinar.
Oh yeah, so this is a picture of the actual placeholder, scan body, everything in the library.
Right, that's all these digital parts which are implemented in the library, but one specific file here is the placeholder file, which is shown here on the left in blue. Yes, and it's an integral and important part of our library, because it generates the hole in the model, the insertion slot for the physical implant analog.
Yeah, so as you see on the model rotating a little bit in the corner there, so it's actually the cavity inside the model where the analog fits. And I think we talked about that in the last webinar. That is the analog itself is actually not important. But what's important here is actually the placeholder file, the light blue one that you said. Okay, I think you have a nicer picture here. Is that what we're talking about?
Yes, right. You see, this is just the physical part, which is green here in this picture, and it's enclosed by the placeholder file like a shell. Yeah. So it's specific adapted to the outer geometry of the analog.
Yeah, exactly. So is the placeholder file that kind of mixes the the scan file together with the cavity for the analog. So it's kind of like a merge between the digital scan file and the actual cavity for the analog.
Yes, and it's precisely aligned to the scan body, which is always the starting point of the intraoral scan.
Exactly.
Yeah. So it's not just the geometry of the placeholder, it's also the adjustment to the scan body part in the library.
Okay, and I think you have a close-up picture of the actual placeholder file. So this is like a cross-section. So now we see what actually goes inside the placeholder file. So this is actually quite detailed cavity or placeholder we have here.
Yes, and you see maybe on this picture that it not just encloses the analog like a negative shape of the outer geometry. No, you have offsets around the analog, but you have specific small areas in this placeholder file which are colored here in green color. Yes, and you see that it's not a large contact area between the placeholder file and the analog. It's focused more on small, well-defined areas, which is much easier to control in your process.
Oh yeah, absolutely. So this is actually the PMA itself. This is how it looks from the library side. This is how it works together with the model builder, model creator software, and merges the actual design together with your 3D printed model in the end.
Right. It just generates the hole in the model. Perfect, to make it easy.
Exactly. Okay, great. So the next bit here, I'm a little intrigued about because I'm not a dental technician, so I need to draw a little on your expertise here. But plaster model and a printed model, are they the same?
Yes, you might be thinking that the 3D model or the printed model is just a digital twin of the plaster model, but it isn't. Yes, because today still a big amount of models are made on the conventional process.
And that's the plaster model.
That's the plaster model. Yeah. And I think it's still, especially for implant model, it's still the benchmark in precision. Yes, even you have a multi-step process chain with contraction of impression material, with expansion of plaster, with maybe limited access of the tray to the patient's mouth, with all this blood and saliva around. Yeah. So on the other hand, we have in many cases more convenient options for digital impressions and model production today, with new materials, with different 3D printers, with different settings, and so on. So I think the 3D model printing is still an evolving technique in the field of implant prosthetics. And according to the current state of the art, the intended use of conventional plaster models and 3D printed models can be viewed differently. Yeah.
So what you're saying is you cannot really replace the traditional plaster model one-to-one with the 3D printed model.
No, not really. Not today, maybe. Yeah. So I think it's fast developing when we're looking in the back 10 years. When we look at 3D printing, it's a fast and a very good development in 3D printing. But today, I would always say it doesn't replace the plaster model one-to-one. It's not a digital twin.
Okay, and I think you actually make some studies on this, you can say. So you actually put in a lot of legwork in this. Can you tell a little bit about that?
Yes, this is called a felt color comparison. That means when you create the model in your CAD software, you get an STL file. Yeah. And this STL file is processed in the CAM software of the 3D printer.
And it is actually nominal. So this is like the perfect, this is what you designed.
This is the perfect model, the perfect base. So this is what you want to have at the end when you printed your model. Yeah. And that's what I did here. I printed the model from this file with different 3D printers, different materials, and then I scanned the printed model with a high-resolution industrial scanner and superimposed both STL files together. And then you see clearly the deviations.
Okay, so we have 3 different pictures here. So what's the difference between each picture? Is it different printers or?
Yeah, I think it's easy to understand. Everything which is green is fine.
Oh, yeah.
So that means 0 micron deviation. Yeah. So you see, the more colorful, the worse, so to speak.
Okay.
Yeah. So you see, these are all 3D printers. Some of them are SLA based with laser light. Some of them, one is DLP printed, and you see that you have, depending on the size of your jaw, you get more and more deviations. Yeah. Especially in the molar region, you see that you get higher deviations, and that's maybe the idea behind to show you that is to see that you never get exactly the SDL file produced like it was from the CAD software. So it's always a little bit different depending on your specific setup in your lab.
Yeah. Okay. Okay. So what we're talking about is actually, well, if you don't have a plaster model and you get an intraoral scan and you do a restoration like a bridge, and you want to bond it, what you're saying is that you shouldn't bond on the 3D printed model, because what we're seeing here is there can be some inaccuracy in the 3D printing. But what should you then do if you don't have this plaster model to actually bond on?
Yeah, so I think, as we just said, so it's depending on a lot of different factors.
Like we have here, yeah.
Yeah. So for multi-implant construction, I would prefer always either direct intraoral bonding, which might be not easy, not for each case the best way, because everything is wet, you have to dry it.
But you actually get like the full passive fit, because that's the...
Yes, you get a full passive fit, so theoretical it's the best process to do so. Yeah. But on the other side, I would say I would prefer the so-called in-bridge bonding. That means that the milled bridge ensures always better precision as the printed model.
So due to the manufacturing of the milling machine is more accurate and stable than your 3D printed result that you saw on your previous slide.
Right. So you are using the bridge like some kind of jig.
Yeah. Exactly.
And then you can bond your hybrid bases in the bridge, without any model, But for sure, that means that your bridge has to be precisely manufactured and that the titanium basis has some kind of self-guiding or self-centering functionality.
Exactly. Yeah. And here on the picture, we have the hybrid base, the non-engaging from Elos, and I think we can cover that in a later webinar. But here we're actually talking about features that actually facilitate this.
Yes, and we maybe just shortly go through this hybrid base. So you see these two antennas.
Our guide grips.
Yes, and this means also that you have a self-centering functionality. So in this case, I always would prefer the in-bridge bonding instead of bonding on a printed 3D model. Yeah. It's okay for single use, I think, for single implant restoration, but multi-implant restoration, I think I would prefer the in-bridge bonding always.
Okay, that's really good. So next up here, we actually have a little history lesson, because the PMA is actually not the first analog from either side. No, we actually started all the way back in 2013, 2014 with the MA. As you can see on the screen, we have the Elos Accurate Model Analog. This is what we refer to as the MA version. And then we have the Elos Accurate Analog for Print Model, which is in short what we call the PMA, or Print Model Analog. And the history is actually that we started when all this actually were a very emerging technology and very new. We started with the MA version. And if you look at the design of these two, they are quite different. You can say that the MA is it's more or less like cylinder. It has a small notch for rotational lock, and then in the top it have these small bumps that actually give like a click feature, so you can click it into the model. Right. And if you look at the PMA, it's way different. It's more detailed. There's a lot of details on it. It's more complicated to manufacture. But what it in theory means is that whereas the MA was a simple cylinder, the cavity that we needed to print had to be very exact for it to actually fit. Whereas with the PMA, we kind of reversed it. So the cavity in the PMA, even though it looks very difficult and so on, it's suitable for the printers to print, and it actually gave the PMA the ability to have the cavity or the play filter, as we talked so much about, to have a little more absorbance of tolerances.
Right. And maybe you remember, and I remember as well as a dental technician, that at the beginning you don't have the possibilities for in-house printing. As you send it to big service centers, and they are worked with industrial 3D printers, which were very expensive, but it's easy to control the process. Yeah. Because you just have 3 or 4 resources to print. Worldwide.
It was more maybe in the beginning of this emerging technology, it was more accurate in what we saw for the first years, because you had like a bigger industrial machines, more control and all that. And they actually, looking back at it, so here we actually have the installation part of the MA. So the idea was that you had this kind of like audible click feature, so it would just snap into the model once it was printed. And this print that we see in the video was exactly made, as you said, from this big print center. That at the time actually gave a really good result. And the material was hard, so you could have this like audible feedback when you clicked it in. What I normally say is, well, things kind of changed when all these more affordable desktop resin 3D printers came on the market.
Right. So it's always the same. I think when the process improves, you also have to improve the product and to adjust it to the new improved processes. That's what we did here.
Yeah, we saw a shift in technology, and we ended up in a situation where you could argue, well, the MA was not actually up or fit for the actual technology enhancement that we saw at the moment, which is why we decided in 2018 to actually design the PMA instead, actually taking into consideration all this new immersion technology that we had. So here it actually is. Here we see the PMA with all the details and all that, and we're gonna cover all the features and the installation part a little later. But what I would like to touch a little bit upon here is actually the tool set, because we have this tool set. I'm gonna go more in depth with that, but that might be a little different from others providers. We have a quite nice tool set here, and there's a little funny history to that, which I actually thought I would share, because the way it actually happened, which is a little funny, but so the head of development here in Denmark, he was actually very fond of going mountain biking, and as we not to. So this is not actual footage, let me say that, but this happens in more than one occasion. And during the development phase of the PMA back in 2018, he actually broke his hand, and you can actually see his X-ray on the screen. And the funny part of this was that even though that he had broke some fingers in his right hand, he was actually able to install the first prototypes of the PMA in a printed model using this tool.
Okay.
And I find that funny, because it just goes to show that even though that actually you can have a really nice and tight fit between the model and the PMA, it requires very little effort to actually install it. And the good thing about this tool is that it actually pulls the PMA into the right position, in the right angle, with very little effort.
Yes, that's a nice story, because for sure you can develop a nice product, a very precise product, but the process behind how to install it is also important. Yes, and so it makes absolutely sense to have a tool for it. And maybe you can compare it also with other processes in the lab. You always need tools to finalize your product at the end. That's how it is.
Yeah, exactly. It's like when you're doing like home repairment, working at home, replacing whatever. If you don't have the right tools, then it takes like twice the amount of time.
That's the reason why. And I think it's a one-time invest just at the beginning. So you can use it for many years.
For sure. It will not get worn. And one of the first questions that we actually got when we actually introduced this, especially the plier tool, that has this O-ring that functions as a spring or elastic band, that people were concerned that it was actually gonna break because it would get fragile or for UV light and so what. But it's actually I don't really remember the specific name for it, but it's like this aerospace grade O-ring, so it will actually last a lifetime. And for now, it surely have. But let's move on to the actual installation phase, because here we see the PMA with the features, and we also see a picture of the cavity or the placeholder, as we talked about before. And I think what's important to mention here is that on top, if you look at that, we have our cutting wedges. So we have these 4 cutting wedges in the top that actually stabilizes the PMA inside the cavity or the placeholder, but it also cuts into the model. So the big difference here between this PMA and maybe especially the MA, as I talked about, but also maybe also other similar product, is that this analog or this PMA is designed to actually cut into the model. So we're actually making all these areas that we highlighted in the placeholder file or the cavity is actually where we have excess material.
Yeah.
Meaning that we're actually printing a geometry where there is excess material for the analog to cut into, and while it can cut into the model, it can also seat very nice and tight every time. So you're not as depending on the variation that might be while doing 3D printing.
Yeah. Right.
And then we have 3 large locking areas in the bottom, meaning that it's really rotational safe. You can really torque it once you install it into the model. It will not rotate, it will not turn, it will not snap. And then in the bottom of these 3 cutting edges, locking areas, we also have cutting edges. So it actually also cuts in the bottom of the cavity, as we see in the picture here. And of course, we have the tool set for it, and we're going to go through the installation process.
Right. And it's color coded.
yeah.
Which is maybe important if you have a box full of PMAs.
Yeah.
You see, this is referring to this platform or to the other platform. So it's following the anodization of the original providers, right?
Exactly. So again, just a small preview. So here we actually see the features compared to the placeholder file we showed earlier, and where you clearly can see these highlighted area and where it will cut.
Yeah.
So I think we should have a look on the installation process, because it comes here. We have this, it's kind of like an instructional video that shows very well how to install the PMA. So we have it here. As you mentioned, we made it especially for 3D printing. It is very much suitable for it. We have the color coding, as you mentioned. It follows the color coding of the implant manufacturer as our scan bodies and so forth.
Mm-hmm.
We have all the nice features here. We have the cutting wedges on top. We have, of course, the implant connection with all the different platforms we support. We have the locking area here on the bottom. You can really see this is a strong locking area, so it will really keep it in place. It will not rotate during work. And we have the thread here on the bottom that actually fits to the installation tool. So what actually the best way to do it is to have your insertion pin and to mount that from the back side of the model. And just place the analog on it, and then pull it into position. So it's a one position only.
Pull it down till it stops.
Yeah, right? And once you get into position and you pull it down and you cannot pull it any further, it actually is a point where it starts cutting. Yeah. And this is where you need the plier tool. So the idea here is that you slide the tool in over, and then turn it, and then you can, just by applying a little bit of pressure, you're pulling the analog, but you're pulling it in the right direction. Yeah, so it's very easy. It's very easy to install it, and you can very easily feel when it buttons out in the bottom of the print, and it's seated. And here again we see the wedges that actually cut into the model, and it's very easy to handle. We also have what we call an insertion screw. I always say that this is optional. It's only if you want to use it. We have the thread in the analog. We can use it if you like to. We have a small magnet on the end of the plier, so it just like snaps into it. And you can use it to make sure that you have your analog in place. If you are in little doubt about the fit of it, you can use it. But I always say that, it's optional.
Yeah. So it's like having belt and braces together.
Yeah, exactly. Exactly. And this instructional guide, it also comes as like a one-pager where it just have all the steps. I've seen many technicians actually use this for the first time, and in my experience, it's only takes like 2 or 3 tries, and then you get a hang of it.
And also you can print it out, put it on your working place, so you can see it in your daily work, so it makes sense, absolutely.
Yeah, it's available on elosdental.com for download. What we also did back in 2018 is, well, with having the MA in mind and this new emerging technology with desktop printers coming out, we thought, well, during the development of the PMA, we actually took and sent prototypes of it to many of the large 3D print manufacturers. And they did a print test. They printed it on their setup to figure out what's the best settings in terms of layer thickness towards the different materials that they had. But also the post-curing, the washing, and all these also important steps that we might not really consider when we started all this with this new technology that is not only the printing, it's also how do you handle the printer.
Yes, and you remember maybe the Wild West just at the beginning of 3D printing, because the post-processing process was not really defined in the lab. So this comes more and more. Now you have more automatically washing stations, curing stations, and all this. And people are often very focused on the hardware side. So what is the layer size and the resolution and all that? But there's much more. You have different light sources, different light exposure, different light intensity. Or different movement, speed of the platform, different viscosity of the material. So a lot of influence factors running around this 3D print process. That's why we need always to test on the single setup. Not having a general fitting or
exactly. And there's a lot of things. One of the things that also strikes me when talking about visiting labs is also, well, it's all about the daily work. It's the maintenance, it's the environment of the printer. There's a lot of factors playing into this, and we did this test, and we did it also not only back in 2018 during the development phase, but we also did it throughout time, where we tried to do it with new printers coming into the market, and the setup is the same. So we send parts to the manufacturer, they do a test run, they figure out, well, what's their best settings. And then we have these printing guides, which also is available on elosdental.com. But basically, it just gives an overview on, well, what's the curing method, what's the cleaning methods recommended, what kind of materials do they recommend, and the layer thickness. And then we actually, together with the manufacturer, we come up with a recommended analog to model offsets, which I know you have a lot on that on our tips and tricks.
Sure. So I think it's a good starting point to have something like that. So it results on your tests here. But anyway, you have a very specific setup always in your lab, and therefore we will come to the tips and tricks section, where you can see how you can modify your settings or influence directly in the CAD software the tolerances of your placeholder file and so on.
Okay, but what do you have for us for the tips and tricks?
Yes, this is about how to influence the offset. And if you see here an Exocad, a model creator, you see here in this window, you see there's a section which is called settings. And you see that you can modify the offset around the physical analog. So 0 means you have 0 micron offset.
So it's exactly as it is in the library, basically.
Exactly as it's in the library, And when you generate your model, then the placeholder file is exactly like in the library. But as we mentioned, we have always shrinkage in the materials, everything like that. So it enables you in the software also to modify the offset.
Okay, so you can actually control it, and this goes back to the accuracy and the tolerances of the printer.
And you see it here with 0 micron. You see that the cutting actions go
the nice overlap here.
Deep in the material, to make the retention between the analog and the model. But you can also modify it here, and let's say going up to 50 micron. And run the model again. You see, now takes some seconds. Yeah, so make it transparent and zoom in. And then you see that the cutting actions are not so much deep in the model than before.
Okay.
So that's a nice way to set up your own offset depending on your process.
Yeah.
Yeah.
Okay. Really nice. It's a really nice feature.
Yeah, you see, this is the hole in the model,
and now you see how that, like the cavity of the placeholder file kind of merges with the rest of the more anatomical part of the model. That's great. That's good to know. So that was the exocad. Here we have a 3Shape.
Yes, we have in 3Shape. It's a little bit different because in 3Shape in our library, if you import our library, then there comes automatically a, let's say, material file inside, which includes a specific offset, and we predefined it as 20 micron.
Yeah.
So
as a starting point.
As a starting point. Yeah. So if you import our library here, as you can see here on the screen,
all the different
you see this
files.
material file, this manufacturing process, which comes in. Yeah. And when you import it and go back in the control panel to the design model, then you can find this manufacturing process.
This is what just was installed.
And there are, I would say, a million of settings.
Yeah. But it's a long list.
Yeah, it's a long list. But the most important thing is the analog space to model setting. Yes, which is, as you can see here, predefined with 20 microns, which is a good starting point. Yeah. Because always it shrinks always, so mostly it's a little bit too tight. Yeah. And now when you create your order in the 3Shape order form, that's what's shown here. So you, as always, you mark your tools and you put a specific abutment on it, like a hybrid base or a pre-milled. And then you come to the step with the model.
Okay, so you select the model.
So now you can select the material and also directly connected with the Elos manufacturing process and the offset. So it comes automatically within.
And I think it's important to mention here that it's actually not locked to the specific. So you can say this material file is a service. So using this will give you a really good first result, but you can also use your own material file.
Yes, it's based on our experience with different printers to set up this standard predefined offset of 20 microns, which should be good for you, but maybe also you have to adjust it a little bit to your process.
Yeah.
And this is also possible in 3Shape. Yeah. So if we go to the next sheet, we can see if you go
to
the model builder application. So you can always modify the setting inside your model building process.
Okay, so while you're doing it, so if you didn't select the right material file, so you can do it here. Okay.
So maybe you select the Elos material file with 20 micron, but later in the printing you see, it's still a little bit too tight. Yes. So you can easily adjust it here by clicking on the setting button on the right and going down, and you see over there also here there's the analog to model space setting, which you can influence. So you can easily create your own offset during the design process in the software.
Okay, interesting. And now we got a model.
Yeah, now we got a model. Now you see the ready-made model. Yeah.
And we have soft tissue and everything. And I think your next tip is about, well, what about this soft tissue and how does that actually work?
Yes, it's more to show how the analog, the placeholder file, now it's really important for the fitting of the PMA. So how is it protected? Especially if you have these gingiva model. Yeah. So if you select the region for the gingiva design, and probably you go below the implant shoulder visit, but the placeholder should be still protected.
Yeah, it's important to mention that the entire design of the cavity or the placeholder file is essential for the analog to work properly.
Yes, and you see it here.
Yeah.
Even it's deeper than the shoulder of the implant.
It has
like analog is still, it's like a cylinder, right?
Yeah.
yeah, it's still protected in your software. And this is very important.
Absolutely.
I think in former versions it wasn't protected.
No,
you have to activate
that.
something or whatever.
Yeah. But
so,
this is true. Yeah.
And I just want to show you. You see, this is a gingiva which from the bottom is more round, round shaped. Yes, but you can also do a flat shape. I know a lot of technicians like to have a flat gingiva mask on the bottom, and that's how you can do it here. So you can go back to the model alignment feature, and then you can select the flat gingiva mask here.
Okay.
And then when you create this mask, it's maybe a little bit different like the process before. So you're marking.
You end up with a completely flat gingiva mask. And is that for printing purposes, or why would you choose this?
Yeah, I think for me it's not so important to have this feature, but probably it comes maybe from the behavior that you are thinking. If you have a flat gingiva mask design, you can put it directly on the printing platform because it's also flat.
So you don't get these support pins and all that.
Yes, but I don't prefer that because the first layers, when 3D printing, the first layers are not so precise, right? Yeah. So that means if you're going directly with the flat side on your printing platform, then you have not this precision in your gingiva mask. So I always recommend to print it upside down.
Okay.
Yes, for sure. Then you have to connect this, but they are easily to cut. Yeah, but you have a very precise surface which just comes in touch with the model.
Okay, so then it fits. Okay, and here we saw in Exocad how with the flat gingiva mask, you also get this protection cylinder around the analog to ensure that it's actually installed correctly.
Yeah.
Okay, good. Okay, good. Because I think actually in this one, I just saw that you actually see, well, what happens if you don't have this cylinder?
Yes, right. So you can see here in this case, when you create the gingiva mask, so you see you have different options here inside the model builder process. I think you know it if you use it each day. Yeah. And if you go into the gingiva creation, so let's see here. Yeah. So now it comes to the interesting part. Yeah, you see there's the gingiva design.
Yeah.
Yes, and if you look at it,
it looks nice.
Yes, you can change. Yes, it's like 3 control levels. Yes, you can cut your gingiva profile from the model, and then what happens here? So if you fade out the gingiva mask like this, you see,
we don't
it's
have
not protected.
No, and in this case, actually, what you would end up with would be a wobbly analog because right now it's not being centered.
And you see here now on the left side, there's
just take the box
specific checkbox, for the protection of the analog, and that's what you have to activate. Yes, and then if you go back, then you see
now we have the cylinder and we have all the features that's actually required to have it installed. Right. Okay, so this is a really important step.
So always activate this checkbox if using a gingiva mask together with the PMA model.
Yeah, great. So Ralph, what's the next trick you have for us?
Yeah, it's the same feature we presented in the first webinar, but now more related to the model creator process. And this is called the switch to implant connection.
Exactly.
Yes, and you sometimes in lab you cannot influence what kind of scan body the attendant is using to scan and send it to you. So probably you get a scan with a different scan body, which you are not familiar with, but you want to use the Elos PMA because you have better results in your printing process or whatever. Yes, and now in this Exocad software, you have the possibility to switch the implant connection. That means starting with a different scan body, but switching to the Elos Analog. Yes, so in the expert mode, you can use that feature, and going back to the wizard, you can create a model with the Elos PMA. Even you start with a different scan body.
Yeah.
So you can combine different libraries together in your process, which makes sense sometimes, yes, because probably the provider of the scan body has no own PMA feature in his library, and then you are running into a dead end.
Yeah, for sure.
In a lab. Yeah. So, and you see here now, this is the Elos PMA placeholder connected with a different scan body. Yeah. Okay. So you can put two libraries together to one. Okay. In this case. Yeah.
Okay, that gives you a lot of flexibility.
Right.
Okay. Well, for the last trick, it's actually we have some giveaways.
Yeah, we talked a lot of the different process of shrinking factors, different light sources, everything like that. And we talked also how can we influence the offset and 3Shape or Accurate software. Yes, and for sure we have these printing guides and everything, but maybe you want to test or set up your own test process. And therefore I thought it could be nice not to start with the designing process in 3Shape or Accurate, but having some STL files which enables you to print directly with different offsets.
Yeah, for your different printers, for your different materials and all that. So we have a collection of small, actually, it's just cubes with this placeholder file in it that have a variation of different sizes. So basically it's just to print it and then do a trial where you see, well, where do we actually gain the best result with your setup?
Yes, and it starts with -10 micron up to plus 50 micron. Yes, and because these are very small cubes, you can easily set up in one building process on one platform. You don't have to create 6 or 5 different models with different offsets and printing each. You just use that cubes, and then you can predefine your best offset. And you see they are marked outside, and so you can use that offset following the tips and tricks section to predefine or to modify your offset.
Yeah, it makes really good sense. And going back to the printing guides, on the flip side of the printing guide, there is like a generic instruction on how to actually put in this value. So
yes,
following also your tips and tricks, how to do it in 3Shape and Accurate, here is displayed a instruction on how to do that.
Right.
Perfect. I think it's
really like nice. A digital giveaway.
It's a digital giveaway. Yeah. Yeah. Digital giveaway to download and use for own self-testing purposes. Great. Yes. Great. Perfect. Well, Ralph, I actually think that this concludes our second webinar on the Elos Accurate Analog for printed models. I enjoyed it.
Yeah, I enjoyed it, and thank you very much to participate with our webinar today.
So thank you for joining, and I hope to see you next time.
Yeah. Bye-bye.